Block 1. The Cosmic Paradox. Is empty space truly empty? Hello, Cosmic Explorers, and welcome back to the channel. Today, we're diving headfirst into one of the most profound and unsettling paradoxes in the entire universe. A mystery hidden not in distant galaxies or exotic black holes, but in the very fabric of what we perceive as empty space. What if I told you that the vast, silent void between stars, the seemingly inert space between galaxies, and even the tiny, unfathomable gaps between the atoms in your own body isn't empty at all? What if, instead, it's a seething, energetic ocean, a quantum cauldron bubbling with activity? This isn't science fiction, it's a terrifying implication of quantum physics, and it sets the stage for a cosmic glitch that, by all accounts, should have already destroyed everything we know. For centuries, our understanding of space was largely defined by what wasn't there. A vacuum was the ultimate absence of matter, a perfect void. But then came quantum mechanics, and it utterly shattered that classical notion. According to quantum field theory, the vacuum is anything but empty. It's a dynamic, vibrant realm where energy fields are constantly fluctuating, even in the absence of any real particles. Think of it like a truly calm ocean on a windless day. From a distance, it looks perfectly still, but if you zoom in, you'll see tiny ripples and movements, even if there's no major disturbance. In the quantum vacuum, these ripples are far more dramatic. This phenomenon is known as quantum fluctuations. At the heart of it lies Heisenberg's uncertainty principle, a cornerstone of quantum mechanics that tells us we can't simultaneously know with perfect precision certain pairs of properties, like a particle's position and momentum, or, more crucially for our topic, energy and time. This energy-time uncertainty means that for incredibly brief moments, energy can spontaneously borrowed from the vacuum, creating pairs of particles and their corresponding antiparticles. These are often called virtual particles because they exist for such an infinitesimally short time before annihilating each other and returning the borrowed energy to the vacuum. It's like a cosmic game of hide and seek, happening billions of times every second in every cubic millimeter of space. This constant ephemeral dance of creation and annihilation means that even at absolute zero, the lowest possible temperature where all thermal motion ceases, space still possesses a minimum amount of energy. This is what physicists call zero-point energy, or ZPE. It's the inherent, irreducible energy of the vacuum itself. Imagine trying to completely empty a jar of air. You can pump out most of the molecules, but you can never truly get rid of the quantum fields that permeate it. This concept isn't just theoretical, it has observable consequences. One of the most famous is the Casimir effect, where two uncharged parallel metal plates placed extremely close together in a vacuum experience a tiny attractive force. This force arises because fewer virtual particles can pop into existence in the narrow gap between the plates compared to the space outside them, creating an imbalance in pressure that pushes the plates together. It's a subtle but undeniable proof that the vacuum isn't nothing. So, if empty space is actually teeming with this quantum energy, if it's a frothing, bubbling brew of virtual particles constantly winking in and out of existence, what does this actually mean for our universe? Why haven't we noticed this immense energy around us all the time? And, more terrifyingly, if this energy truly exists on such a fundamental level, why hasn't it already caused an unimaginable catastrophe? This invisible, omnipresent energy, a core prediction of our most successful physical theories, leads directly to one of the biggest, most mind-bending, and, indeed, most terrifying paradoxes in all of science. It's a paradox so profound that it challenges our very understanding of existence, threatening to unravel the cosmic fabric and reveal a universe that, by all logical deduction, should not be here. We are standing at the precipice of understanding a fundamental glitch in reality, and the implications are universe-shattering. Block 2. The universe's biggest glitch, why everything should have exploded. We've established that what we perceive as empty space is in fact a vibrant, energetic quantum foam, constantly generating and annihilating virtual particles, giving rise to what's known as zero-point energy. Now, let's confront the truly mind-bending and terrifying consequence of this idea, the vacuum catastrophe. This isn't just a theoretical curiosity, it's a colossal discrepancy between what our most successful theories predict and what we actually observe in the universe. It's often dubbed the biggest error in physics, and for good reason. Here's where Einstein steps in. His theory of general relativity fundamentally changed our understanding of gravity. It taught us that gravity isn't a force pulling objects together, but rather a manifestation of space-time itself being warped and curved by mass and energy. The more mass or energy you pack into a given volume, the more space-time curves around it. This curvature dictates how everything moves, including light. Now, if empty space is truly permeated by this inherent zero-point energy, as quantum field theory suggests, then this energy itself should act as a source of gravity. It should be curving space-time. And this is where the wheels come off. When physicists attempt to calculate the total energy density of the quantum vacuum, essentially how much energy is packed into every cubic centimeter of empty space, the numbers are absolutely staggering. Our best quantum field theories predict an energy density so astronomically high that it's almost impossible to comprehend. We're talking about a vacuum energy density that should be equivalent to a mass of roughly 10 to the 93 grams per cubic centimeter. To put that into perspective, that's enough energy to create a black hole larger than our entire solar system in every single cubic millimeter of space. If this theoretical calculation were correct, the gravitational effects would be catastrophic. This immense omnipresent energy should have done one of two things, or perhaps both, almost instantaneously after the Big Bang. It should have either caused the entire universe to gravitationally collapse into an unimaginably dense black hole, or it should have generated such an incredibly powerful repulsive force that it would have ripped the universe apart faster than the blink of an eye, preventing any stars, galaxies, or even atoms from ever forming. In either scenario, our universe as we know it would simply not exist. It would be a fleeting, violent quantum hiccup gone before it even had a chance to begin. This is the infamous 120 orders of magnitude discrepancy. It means the observed vacuum energy, which we detect as dark energy causing the universe's accelerated expansion, is smaller than the theoretically predicted quantum vacuum energy by a factor of 1 followed by 120 zeros. To illustrate how absurdly large this difference is, consider this. The ratio of the size of the observable universe to the size of a single proton is about 40 orders of magnitude. The discrepancy in vacuum energy is 3 times difference. It's not just a small error, it's a fundamental crisis at the heart of modern physics, a glaring contradiction that points to a profound gap in our understanding of how the universe truly works. So, the profound puzzle stands before us. If the very fabric of space is a boiling cauldron of quantum energy, and if that energy should, according to our most trusted theories, exert such an overwhelming gravitational influence, then why are we still here? Why has our universe not succumbed to this cosmic glitch? Why does it exist at all in its vast, relatively empty, and expanding? This isn't just a theoretical debate for physicists, it's a fundamental question about our very existence, a terrifying reminder that our current models of reality are incomplete and perhaps profoundly flawed. The universe seems to be playing a trick on us, hiding its most powerful secret in plain sight. Block 3. How are we still here? Unraveling the cosmic mystery. Given the terrifying implications of the vacuum catastrophe, the idea that our universe should have either imploded or been torn to shreds by the immense energy of empty space, The very existence of stars, galaxies, and indeed ourselves stands as a profound and bewildering mystery. How have we managed to survive this cosmic glitch? This question lies at the cutting edge of physics and cosmology, prompting scientists to explore a variety of ingenious, if sometimes speculative, theories to reconcile the colossal predicted vacuum energy with the incredibly tiny amount we actually observe. One of the most direct ways physicists try to address this is through the cosmological constant problem. The cosmological constant, introduced by Einstein and later revived, is a term in his equations of general relativity that represents the energy density of empty space. Observations tell us this constant is tiny, a small positive value that accounts for the accelerating expansion of the universe, what we now call dark energy. But quantum field theory's prediction for this value is, as we've seen, astronomically larger. So, where did all that theoretical vacuum energy go? One elegant, though currently unproven hypothesis involves supersymmetry. This theory posits that for every known particle in the Standard Model, there exists a heavier superpartner particle. If supersymmetry were a perfect symmetry of nature, the vacuum energy contributions from regular particles would be exactly canceled out by the contributions from their superpartners. The problem is we haven't found any superpartners yet at colliders like the LHC, meaning if supersymmetry exists, it must be a broken symmetry. The breaking of this symmetry could leave a small residual vacuum energy, but it's still incredibly difficult to tune this breakage to exactly the tiny value we observe for dark energy. It would be like trying to balance a pencil on its tip for billions of years. Possible, but incredibly improbable without a deeper mechanism. Another compelling, albeit controversial, idea is the anthropic principle. This principle suggests that the reason we observe the universe to have the physical constants it does is simply because if they were any different, we wouldn't be here to observe them. This often ties into the concept of a multiverse, where our universe is just one of an infinite number of universes, each with slightly different physical laws and constants. In this vast cosmic landscape, only a tiny fraction of universes would have a cosmological constant small enough to allow for the formation of stars, galaxies, and ultimately life. We just happen to live in one of those lucky universes. While intellectually satisfying to some, it's difficult to test empirically, making it a philosophical argument as much as a scientific one. Then there are more radical proposals, such as modifications to our understanding of gravity itself. Perhaps Einstein's general relativity, while incredibly accurate on solar system scales, needs to be adjusted or extended on cosmic scales. Or perhaps the very act of observing or measuring the vacuum energy somehow collapses its true immense potential into the tiny value we see, a concept that delves into the most esoteric corners of quantum mechanics. Some theories of quantum gravity, like string theory or loop quantum gravity, aim to provide a more fundamental description of space-time and matter, hoping that a unified theory will naturally resolve the cosmological constant problem, predicting a low vacuum energy from first principles. Ultimately, the small positive value of dark energy that we observe today, a form of vacuum energy, it's just an incredibly tiny fraction of what quantum theory predicts. The universe is indeed accelerating its expansion, driven by this mysterious force, but it's doing so gently, not violently ripping itself apart. This profound discrepancy remains one of the greatest unsolved puzzles in physics, a stark reminder that our most powerful theories, quantum mechanics and general relativity, are still incomplete. They are like two magnificent pieces of a puzzle that don't quite fit together in this crucial area. The search for a solution continues, pushing the boundaries of human knowledge and reminding us that the universe's greatest secrets might indeed lie in the emptiest of spaces, holding the key to why anything exists at all. So, what do you think? Is the universe's survival against this cosmic glitch a matter of pure chance, or is there a deeper unknown law of physics at play? Write in the comments. Subscribe to learn more, and see you soon.